Hey everyone. Today we'll be talking about auditing zkEVM, overviewing its attack surfaces, and showcasing some of the findings we had on Polygon zkEVM audit. I think the main purpose of the talk will be to compete for most boring talk on ECC. So yeah, let's try win that. So my name is Vahe. Some people know me by my nickname Cameo. I've been doing cybersecurity for around a decade, doing web and binary exploitation before that. I really like playing CTFs. You can tell it by my t-shirt. And I'm co-founder at Hexens. We do all the cool stuff, blockchain audits, cryptography, ZK, of course, and we also develop security products. So zkEVM is growing crazy. A lot of great projects developing zkEVMs like Polygon, Scroll, zkSync, Tyco. Well, the high-level overview, just in a couple of words, like zkEVM takes as input the old L2 state and some transactions, and outputs like the new L2 state and generates the proof that you can use on the layer 1 to change the state. So today we'll be more talking about the Polygon as we did the audit. It's a huge code base. It has around 40 components, but our main focus today will be the prover as of the heart of the zkEVM. So Polygon had this interesting approach of mimicking microprocessor and like having a hardware layer and then an assembly language that works on it. And on top of that, you have a ROM, basically zkEVM, written in the zkISM level. So the hardware is called PIL. It's a domain-specific language for defining state machines with its registers as polynomials. That's basically like the main constraint part of the zkEVM. And like generally speaking, the PIL can be used not only for the zkEVM. You can just write your own state machines and have them provable. So yeah, on top of that, you have the zkISM that works with the hardware, and using this zkISM, you just emulate the EVM, and you automatically get the zkEVM. So what kind of bug types are we looking at in terms of zkEVM audits? So of course, it's mainly the soundness and completeness issues. So soundness is basically that you cannot prove any incorrect statement, and completeness will be that any correct statement should be able to be proven. So in terms of like applied security, auditors are more likely to look at soundness issues because that's the ones that bring you like to bigger impact, like proving that you have much more Ethereum balance that you have actually, and completeness is more like mostly like denial of service attacks. So there are lots of layers where you can find these bugs. Actually, the short answer is everywhere. You gotta look everywhere. There might be discrepancies between all the layers. But the ones worth noting definitely is the circuit design. So whether you have implemented all the constraints that your program assumed. Another one is, if you're doing zkEVM, you'll be implementing or deriving a lot of cryptographic primitives. And it's very easy to break something there. We can see a lot of weak fiat summary transformations reported before that, like discrepancies from papers and etc. So another very important part is the program logic vulnerability. So basically, whatever you're proving, it should be working, right? And it can have like logic vulnerabilities. And of course, unintended discrepancies between EVMs and zkEVMs. Let's not forget about the rest of type of attacks that are not directly connected to zk, but you still have them as you have some smart contracts. You can have some vulnerabilities there, some misalignments in economics, or you still have nodes, some attack on nodes. So today I'll be talking about a couple of bugs on different layers. So the one is on program logic layer, and the second one is on the constraint level, rather. But I will not be too technical on them as we're quite limited on time. But you can scan the QR, get the full audit report, and take a look at the details there. So the first one is the memory management bug that we found. So basically how zkEVM handles the dynamic memory in EVM. So you have stack, you have dynamic memory where the mstore mload happens. And for zkEVM, it's also following this microprocessor logic, and it has one physical memory. And for him, all these context-based stacks and dynamic memories are like virtual memory and just map with a certain formula to a real address, like physical addresses, right? One important thing about this context, so every message has its context. So when you create an external call, it creates a new context so you don't overlap the memory. And one important thing here is that context also includes the global and local variables. So not only stack and dynamic memory, but also that. And the PIL uses a special register called context, CTX, to be sure that you do not overlap there. But eventually we managed to find a bug in the identity precompile implementation, where through a specifically crafted transaction, when you call this precompile, you can actually corrupt the CTX to get the value 0. And the most interesting part here is that CTX with value 0 is a special context. You cannot get like CTX 0 if you're executing transactions or making calls. Like the main difference is that for the context 0, instead of local variables, you store them the global variables. The global for the zkEVM, like old state root or old account input hash and other stuff. And on the other hand, like if we will be in the message, we'll have like gas limit, destination address, and that kind of stuff. So actually corrupting the CTX to 0, we have a very interesting thing here, is that we have a double reference between these values. So for example, in zkEVM, when we will be querying gas limit, we'll be actually getting the old state root, right? So for you that had some experience with binary exploitation, it's like classic double reference bug. But let's see like how we can leverage this bug to actually, let's say, make some money. Eventually we found the function in zkEVM called handle gas. That's basically a function that credits sequencer for the transaction fee, basically just multiplying gas price by gas limit and crediting it to the sequencer balance. And as you can see, like the gas limit here will be the old state root, which is a hash value, and it's almost guaranteed always to have like super big absolute value in it. And an important part here, oh shit. Yeah, an important part here is that we have an assertion of this multiplication not to overflow. So we need to put the gas limit equal to 1. And at that time, like the gas price equal to 1, and the gas limit will be old state root, and will be credited like enormous amount of ether to sequencer. But right now there's only trusted sequencer, but yeah, further on Polygon is going to have like decentralized sequencers. So the next one will be on the constraint level. The zkESM has an interesting opcode. It's called jump negative, jump n, as you can see on the right side. So when the result of the operation is negative, it jumps to the label mentioned. And you might not fall really into these formulas, but the thing is that how PIL handles this, it has a selector called isNegative. And when the result is not negative, it's 0. When the result is negative, it's 1. And this isNegative polynomial eventually flows down into the last formula of the next extraction constraint, like program count, zk program counter, as you can see. But the thing is that we were missing a constraint here, that the isNegative should have binary values 0, 1, but we don't have this. You can see the constraint. You don't have that constraint there. So using this, we actually can leverage a very interesting thing. Wherever our result is negative, we can using like very easy derived formula for how to put the is negative and operation values, we can jump to any label and not just the label mentioned here, like fail assert. We can jump to any line in the firmware. This is also quite similar to binary bugs. Like we have a execution flow hijack, and we gotta find now a gadget chain, so where can we jump it? So it continues the execution in a way that first we don't break it, we don't break any assertion, otherwise it will be unprovable, and we don't need that, that will be meaningless attack. And the second one, to get the most important impact, like for the hacker or attacker to have some arbitrary balance on that. And eventually we found a jump chain that you can use. It ends up with a refund gas function. It goes through like delegate call, the compute gas and refund gas. And eventually the refund gas, it is the function that refunds the caller the unused gas amount. And we use these 3 lines that it sets the balance, and using these first 2 calls that actually adjust the registers in a way that we need them to work there. So eventually we can credit arbitrary amount of either to anyone using this. So another important thing about analyzing this kind of projects is when you work with this kind of DSLs or even like PIL or even the zkEVM, it's always really a good idea to have a static analysis, because you have lots of polynomials, you have lots of constraints, and you really can improve your audit with automation. But the PIL is a novel language, so we don't have a SEST. And eventually during the audit we write our own one. We called it Pillar, and we had a couple of really very interesting features in them. The first one is the constraint templates. You can write a template of constraints you want to find or to exclude them. You can see on the example, you just write the PIL, like there is one polynomial a multiplied 1 minus a equals 0, and the template engine will find all the constraints that look like this. And also we taint all the committed polynomials. So one nice example that we used and really found missing constraints like this. So we parsed the executor for polynomials that are actually signed only with 0 and 1 values. And then we used this template engine and polynomial tainting to find the polynomials that don't have this kind of constraints, and we found a couple of them. So we've open sourced that, but it's like still like a play tool, so highly encouraging all of you, you can fork, contribute, it will be nice. So last but not least, as we're really limited on the time, so for all you security experts or developers that like to contribute to Web3 security, we're launching our Web3 security platform. It has a dope domain like r.xyz, where please go ahead and register on a wait list, because right now we'll be in a closed stage. There'll be a lot of really dope features and tools that will help you find bugs. One of the important ones I like to mention, so a couple of speeches ago, it was mentioned that we see a lot of bugs repeating, like the same kind of bug repeating itself over and over. So we'll be closing that issue, we'll be addressing that issue with one of our tools, and I think it will be great. So yeah, stay safe, find bugs, prevent hacks. Thank you.
Yeah. 1, 2. All right. So we're going to have a small Q&A. Time for 1 or 2 questions.
Hello. Thank you for the talk. It seems like the findings that you have in this audit were very specific. Was there any methodology that you followed? Was there any focus on specific types of invariant that you used during this audit? Can you elaborate a little bit on that?
Yeah, so I believe that whenever you'll be auditing a zkEVM, most likely your findings will be very specific to that zkEVM implementation, because whatever we talked about, like the scroll, the Tycho, the zkSync, the Polygon, all have like different approaches, different architectures, different tech stack. So I would say that the main thing that you need to understand to go through like a zk audit, the first thing is to understand that it's not like execution-based program. It's rather constraint-based program, so you will, not everything that you see that is written is actually checked and like working like you expected, because you'll be having a lot of free input coming out of the executor, and you need to check all this in constraints. So that's a bit like a shift of mindset between auditing like a classic program, let's say, and a zk provable one.
Any further questions? Nope. Well, yeah, if you have any questions, feel free to reach out to him, and I think we can close it here.
Okay, thank you.
Thank you.